4 billion years ago, you could have surfed a wave 1 kilometer tall. The moon hung in the sky 10 times larger than today, and the ocean didn't just rise and fall, it exploded across continents twice a day like a planetary heartbeat made of water moving faster than a bullet train. Picture standing on an ancient shoreline, watching the horizon. You'd see it coming from 50 kilometers away, a wall of water taller than the world's highest skyscrapers, racing toward you at 300 kilometers per hour. You'd have 10 minutes to run. You wouldn't make it. This wasn't a tsunami. This wasn't a storm. This was high tide, and it happened twice every single day. What if the gentle tides we see today are just the dying whisper of forces that once shaped continents, boiled oceans, and created the very chemistry of life itself? What if everything calm and predictable about our planet exists only because the moon, our constant companion, has been slowly abandoning us for 4.5 billion years? Here's something most people don't know. We can measure exactly how fast the moon is leaving us. Since 1969, when Apollo astronauts placed laser reflectors on the lunar surface, scientists have been bouncing laser beams off the moon and timing how long they take to return. The measurement is absurdly precise. We can track the moon's position to within a millimeter, and what those measurements reveal is unsettling. The moon is receding from Earth at 3.8 centimeters per year. That's about the rate your fingernails grow. Doesn't sound like much, does it? But run that clock backward. The moon is currently 384,000 kilometers away. Reverse time at roughly 4 centimeters annually, accounting for variations in recession rate. And you find something extraordinary. 2 billion years ago, the moon was half as far away. 4 billion years ago, it was a quarter the distance. At the moment of its formation, 4.5 billion years ago, the moon orbited at roughly 15,000 kilometers from Earth's surface. Let me put that in perspective. The International Space Station orbits at 400 kilometers. Geostationary satellites orbit at 35,000 kilometers. The moon, at its birth, orbited at 15,000 kilometers, closer than our communication satellites today. From Earth's surface, it would have appeared not as the small disk we see now, covering half a degree of sky, but as an enormous sphere filling 50 degrees of your field of vision. If you could somehow stand on that primordial Earth and look up, half the sky would be moon. It would loom overhead like a vast, cratered ceiling, visibly moving, close enough that you could make out individual craters and mountain ranges with the naked eye. Before we dive deeper into this story, please consider subscribing and liking this video. Your support truly helps us continue this work, and I'm genuinely grateful you're here. Thank you. And that mass did press down, not metaphorically, literally, through gravity. Tides, as we experience them today, are gentle affairs. Even in the Bay of Fundy, famous for having the world's highest tides, the water rises and falls about 16 meters. Most coastlines see tidal ranges of 1 to 3 meters. The mechanism is straightforward. The moon's gravity pulls on Earth's oceans, creating a bulge of water on the side facing the moon, and another on the opposite side through inertia. As Earth rotates through these bulges, we experience high and low tides. But here's the critical detail that changes everything. Tidal force doesn't scale linearly with distance. It scales with the inverse cube of distance. If you halve the distance to the moon, you don't double tidal forces, you increase them eightfold. If the moon is 4 times closer, tidal forces are 64 times stronger. At 15,000 kilometers distance, the tidal forces acting on Earth's oceans would have been roughly 200 times stronger than they are today. 200 times stronger. What does that actually mean for a planet? It means that if today's tides in the Bay of Fundy reach 16 meters, those primordial tides would have theoretically reached 3 kilometers. But that calculation is misleading because it assumes the ocean would behave the same way at all scales. It wouldn't. At that scale, water doesn't slosh, it detonates. The tidal bulge would have been so massive, so energetic, that as Earth rotated beneath it, coastlines would experience something closer to a twice-daily impact event. The kinetic energy involved would be comparable to the largest volcanic eruptions happening continuously, everywhere, twice per day. We have evidence that this happened, not speculation. Evidence written in rock. In the Flinders Ranges of South Australia, there are sedimentary formations called tidal rhythmites. These are rocks that formed from tidal sediments, layers of mud and sand deposited by ancient tides. Each layer represents a single tidal cycle. You can count them like tree rings, daily layers, monthly cycles where spring and neap tides alternate, annual patterns. Geologists have studied rhythmites from 620 million years ago, and what they found is extraordinary. The layering pattern proves that Earth's day was only 21 hours long back then. Not 24 hours, 21. Earth was rotating faster, and the tidal range recorded in those rocks was significantly larger than anything we see today. Tens of meters, even in mid-ocean settings. This is the first piece of hard evidence. Ancient rocks preserve the moon's distance by recording day length. 21-hour days, 620 million years ago. But Earth is 4.5 billion years old. If Earth has been slowing continuously due to tidal friction, we can extrapolate backward. 3 billion years ago, Earth's day was probably about 15 hours. 4 billion years ago, perhaps 10 to 12 hours. The early Earth spun like a top, and every single one of those short days contained 2 monstrous tidal cycles. Why was Earth spinning so fast? And why has it been slowing down? The answer is tidal friction. As the moon pulls on Earth's oceans, creating those tidal bulges, Earth rotates underneath them. But the bulges don't stay perfectly aligned with the moon. Friction from water moving over the seafloor causes the bulges to drag slightly ahead of the moon's position. This misalignment means the tidal bulge pulls back on the moon gravitationally, speeding up the moon's orbit. As the moon speeds up, it moves to a higher orbit. This is basic orbital mechanics. Conservation of angular momentum demands this. If the moon gains angular momentum, Earth must lose it. Earth's rotation slows down. The moon moves away. This process has been happening for 4.5 billion years, every single day, without pause. But here's where it gets interesting. The recession rate isn't constant over geological time. When the moon was closer, tides were stronger, friction was more intense, and energy transfer was faster. The moon receded much more quickly in the distant past. Recent modeling suggests that for the first billion years after the moon formed, it might have receded at rates 10 to 100 times faster than today. The moon didn't just drift away slowly over billions of years. In the beginning, it fled, powered by the apocalyptic energy of oceanic tides grinding against a young, barely solid planet. And in those early eons, when days were 10 hours long and the moon raced across the sky 4 times daily, something else was happening. Something connected to wet-dry cycling in tidal zones. We'll come back to that because it's the key to everything. Let's talk about what early Earth actually looked like. At 15,000 kilometers distance, with the moon appearing as a monstrous disk covering a sixth of the sky, tidal forces would flex, not just the oceans, but Earth's crust itself. Earth tides, the solid planet deforming under gravitational stress, would have been meters high. Think about that. The entire planet would bulge toward and away from the moon twice per rotation. Imagine the ground beneath your feet, rising and falling several meters twice a day. Imagine every earthquake zone on Earth triggering simultaneously, twice daily, forever. The tectonic stress would have been incomprehensible. Volcanic activity would have been constant. Any primordial crust trying to solidify would have been fractured, remelted, pulverized by these relentless gravitational forces. And the oceans, they would have been hot, not just from residual planetary formation heat, but from tidal heating, the same mechanism that keeps Jupiter's moon Io volcanic and Europa's subsurface ocean liquid today. Tidal flexing generates heat through friction. When you bend something back and forth repeatedly, it heats up. This is basic physics, but at planetary scale, the effects are staggering. Earth's oceans, sloshing violently twice every 10 hours under lunar tides 200 times stronger than today's, would have been heated continuously by their own motion. Estimates suggest early Earth's ocean temperatures could have been 60 to 80 degrees Celsius on average, with tidal zones reaching boiling point during the most intense tidal surges. The planet was a pressure cooker. High tide was a scalding flood covering thousands of kilometers. Low tide exposed steaming, mineral-rich mudflats that would bake under the young sun for hours before being inundated again. The surface was being ground down, literally, by the moon's gravity. Rock fractured, minerals dissolved. The crust couldn't stabilize because it was being flexed meters up and down twice daily. And in this chaos, in these violent oscillations between ocean and exposed land, something remarkable was about to happen. But to understand what, we need to understand where the moon came from in the first place. About 4.5 billion years ago, roughly 50 million years after the sun ignited and the solar nebula began to coalesce into planets, a Mars-sized protoplanet, given the name Theia by astronomers, collided with the young Earth. Computer simulations suggest it was a glancing impact, not head-on. Theia approached at an angle of roughly 45 degrees at speeds of several kilometers per second. The energy released was staggering, equivalent to billions of nuclear weapons detonating simultaneously. For perspective, the impact that killed the dinosaurs 65 million years ago released energy equivalent to about 100 million megatons of TNT. The Theia impact released energy equivalent to hundreds of billions of megatons. It was an event capable of vaporizing oceans, melting continents, and nearly destroying the planet. Theia's iron core merged with Earth's core almost immediately, sinking through the lighter mantle material within hours. But the rocky mantles of both bodies, the outer shells of silicate rock, were vaporized and ejected into orbit. Within hours, Earth was surrounded by a ring of molten rock and vaporized silicates, glowing white-hot, stretching tens of thousands of kilometers into space. This debris ring would have been visible from interstellar distances, a glowing disk of destruction orbiting a wounded planet. This ring didn't last long. Over thousands of years, it cooled. Gravitational interactions caused the material to coalesce. Most of it formed a single body, the Moon. The Moon assembled quickly by geological standards. Within a century to 1,000 years, it had aggregated from countless smaller moonlets orbiting in that debris disk. And when it finished forming, the Moon was right there, orbiting at roughly 15 to 20,000 kilometers, made from the same material as Earth's mantle, because that's literally what it was. Pieces of Earth's outer layers reassembled in orbit. This is why lunar rocks and Earth rocks have nearly identical isotopic compositions. They're siblings, forged in the same catastrophic event. Every other body we've studied, Mars, asteroids, comets, has a distinct isotopic signature indicating where in the solar nebula it formed. Each region of the protoplanetary disk had slightly different ratios of oxygen isotopes, titanium isotopes, chromium isotopes. These ratios are fingerprints. Mars has one fingerprint, Vesta has another, comets have a third. But the Moon's fingerprint is indistinguishable from Earth's. The only plausible explanation is that the Moon formed from Earth's mantle material ejected during the giant impact. And here's a remarkable detail that makes this story even more precise. If you rewind the Moon's orbital history and account for faster early migration due to stronger tidal forces, you find that the Moon formed almost exactly at what's called the Roche limit. The Roche limit is the distance at which tidal forces from a parent body become strong enough to tear apart a satellite held together only by its own gravity. For a rocky moon orbiting Earth, the Roche limit is about 2.5 times Earth's radius, roughly 15 to 18,000 kilometers. If the Moon had formed inside this limit, it would have been ripped apart immediately, forming rings like Saturn's instead of a consolidated moon. If it formed too far outside, the debris wouldn't have coalesced efficiently. It would have remained as separate moonlets that might have eventually fallen back to Earth or drifted away. The Moon exists, in other words, because the giant impact ejected material at precisely the right distance. A few thousand kilometers closer, and Earth would have rings instead of a moon. A few thousand kilometers farther, and the Moon might not have formed at all, or might have formed much later from material that gradually spiraled inward. Either way, the result would have been different. And without a large, close moon, the tides that would shape Earth's destiny would never have existed. At that distance, immediately after formation, the Moon's tidal forces would have been almost unimaginable. Earth, still partially molten from the Theia impact, would have experienced tidal bulges, not of water, but of liquid rock. The entire planet would have deformed by kilometers, twice per rotation. And Earth was rotating fast, perhaps once every 5 or 6 hours immediately after the impact, because the collision added angular momentum to Earth's spin. The Moon would have appeared to race across the sky, rising and setting 4 times a day, each time dragging a mountain range-sized bulge of molten rock across the planet's surface. This phase is called the magma ocean era. For the first few million years after the Moon formed, Earth's surface was an ocean of liquid rock, kept molten partly by residual heat from the impact and partly by continuous tidal heating from the nearby Moon. The Moon was grinding Earth's surface like a mortar and pestle, generating enormous amounts of frictional heat. Eventually, over tens of millions of years, the surface began to cool despite the tidal heating. The first crust formed, thin, unstable, constantly broken and reformed by tidal stresses. This crust was fragile. Every tidal cycle would have fractured it, allowing magma to well up through the cracks. For tens of millions of years, Earth might have had solid crust only in low tide regions, while high tide zones remained perpetually molten, creating a bizarre planetary surface where the ground alternated between solid and liquid, depending on where the moon was in the sky. And through all of this, the moon was receding, because tidal friction in a molten planet is far more efficient than in a solid one with oceans. The energy dissipation rates were enormous. The moon might have migrated outward at meters per year during this phase, not centimeters. Within 10 million years, it could have moved from 15,000 kilometers to 50,000 kilometers. By the time stable oceans formed, around 4.4 billion years ago, based on evidence from zircon crystals, the moon had already moved far enough that tides, while still enormous by today's standards, were no longer melting the surface. Earth had cooled enough for liquid water to condense and remain stable. And with liquid water came the next chapter of the story. Because now we have a planet with oceans. We have a nearby moon creating tides hundreds of times stronger than today. We have a surface that's cooling, forming continents and coastlines. And we have something that didn't exist before: tidal zones, places where ocean meets land, places where water advances and retreats on a regular, predictable schedule, places where chemistry can happen in ways impossible anywhere else in the universe. This is where life begins. Imagine a coastline 4 billion years ago. The moon is now perhaps 50,000 kilometers away, still much closer than today, but far enough that Earth's surface has solidified. Days are about 10 hours long. Every 5 hours, the tide comes in. And when it comes in, it doesn't creep up the beach like tides today. It arrives as a surge, a wall of water several hundred meters high, racing inland at speeds that would dwarf modern tsunamis. This tidal wave, not a wave caused by an earthquake, but the actual tide itself, floods hundreds of kilometers inland, covering everything in hot, mineral-rich seawater. Then, 5 hours later, the tide retreats, and it retreats just as dramatically. Within hours, all that water drains back into the ocean, leaving behind vast expanses of wet, muddy terrain. The sun beats down. The surface temperature is high. Earth's atmosphere is thicker with carbon dioxide, creating a greenhouse effect, and there's no ozone layer yet to block UV radiation. The water begins to evaporate. Within an hour or two, shallow pools that formed in depressions and basins start to concentrate. Water molecules escape into the atmosphere, but dissolved minerals, salts, and any organic molecules present remain behind. The concentration increases 10 times, 100 times, 1,000 times. In the deepest pools, evaporation might be slower, but in shallow pools only centimeters deep, the water disappears entirely, leaving behind a dried crust of concentrated minerals and organics. And then, 5 hours later, the tide returns. Water floods back in, rehydrating everything, dissolving the concentrated residues, allowing molecules to move and interact in solution. Then, it retreats again. This cycle repeats twice every 10-hour day, 730 times per Earth year, 730 chances for chemistry to happen, 730 cycles of concentration and dilution. And this process continues for millions of years, across thousands of kilometers of coastline, in billions of individual pools and basins, each one a unique chemical environment. This is wet-dry cycling. And it turns out this process is almost certainly how life began. We'll explore exactly why in detail, but first we need to understand the different types of tidal environments that would have existed because they weren't all the same. Each type would have offered different chemical conditions, different opportunities for the chemistry of life to emerge. Shallow tide pools formed in depressions in rock, perhaps only meters across and centimeters deep. These would experience the most extreme wet-dry cycling. Water would flood in, then evaporate almost completely within hours. Concentration factors in these pools could be enormous, 10,000-fold or more. These pools would also experience the widest temperature swings, heating up dramatically when exposed to sunlight, cooling when flooded. They'd be rich in whatever minerals the local rock provided. Basalt coastlines would provide iron, magnesium, calcium. Granite areas would provide different chemistry. Every pool would be slightly different. Deep tidal lagoons formed in larger basins, perhaps kilometers across and tens of meters deep. These wouldn't dry out completely between tides. Instead, they'd experience more gradual concentration as water slowly evaporated over multiple tidal cycles. The chemistry here would be more stable, less extreme. Molecules would have more time to interact without being completely desiccated. These lagoons might accumulate layers of sediment over time, creating stratified environments where different chemistry happened at different depths. Estuaries formed where rivers met the ocean. Here, fresh water from rivers mixed with salt water from tides. This created unique chemistry, salinity gradients, pH gradients, temperature differences. Fresh water would bring dissolved minerals from continental weathering. Salt water would bring ocean chemistry. The mixing zone would be dynamic, constantly shifting with each tide. Some researchers think estuaries might have been especially important for early life because they provided such diverse chemical conditions in close proximity. And there's another type of environment that might have been crucial: hot springs in tidal zones. Early Earth was volcanically active. Hydrothermal vents were common. Now imagine a hot spring near a coastline where geothermally heated water emerges from cracks in rock. Twice a day, tides flood over this area, mixing hot spring water with ocean water, creating temperature gradients and chemical gradients. These zones would have been especially energetically favorable for certain types of chemistry. The combination of heat, mineral-rich water, and tidal cycling might have been ideal for driving chemical reactions that wouldn't happen otherwise. All of these environments shared one critical feature. They concentrated organic molecules, and concentration is absolutely essential for the origin of life. Here's why. In a vast, well-mixed ocean, organic molecules are incredibly dilute. Amino acids, nucleotides, simple sugars, whatever prebiotically plausible organic compounds existed on early Earth, would be spread throughout cubic kilometers of water. The concentration might be parts per million or parts per billion. At those concentrations, molecules almost never encounter each other. They float around independently. They might collide randomly once in a million years. No complex chemistry can happen because the reactants never meet. But concentrate those molecules 1,000-fold, and suddenly they're bumping into each other constantly. Concentrate them 10,000-fold, and reactions that would take millions of years in dilute solution happen in hours. This is basic chemical kinetics. Reaction rates depend on concentration. Double the concentration, and you roughly double the reaction rate for many reactions. Increase concentration by a factor of 10,000, and reaction rates increase by factors of millions or billions for reactions involving multiple molecules coming together. Tidal pools provided this concentration mechanism naturally, repeatedly, everywhere. No other planetary process does this as effectively. Volcanic pools can concentrate molecules through evaporation, but they're rare and often too hot for organic chemistry. Ice can concentrate molecules at grain boundaries, but early Earth was too warm for extensive ice. Ocean spray can create concentrated droplets, but they don't last long and don't accumulate. Tidal pools are perfect. They're everywhere along coastlines. They concentrate reliably on a predictable schedule. They provide a huge range of chemical conditions depending on local geology, and they persist for geological timescales. And in 2022, researchers at the University of Washington demonstrated experimentally that this process works. They took a mixture of nucleotides, the building blocks of RNA, and subjected them to repeated wet-dry cycles in the presence of certain clay minerals, particularly montmorillonite. This clay is common on Earth and would have been abundant in early tidal environments. It has a layered structure with negatively charged surfaces that attract and bind nucleotides. What happened was remarkable. During the wet phase, nucleotides would bind to the clay surface, becoming concentrated in a thin layer on the mineral. During the dry phase, as water evaporated, the nucleotides were pressed together even more tightly, and the chemical conditions shifted to favor condensation reactions. Reactions where smaller molecules join together to form larger ones, releasing water. In this case, nucleotides began linking together to form chains, RNA polymers. The researchers produced RNA molecules up to 200 nucleotides long. That's astonishing. 200 nucleotides is long enough for an RNA molecule to fold into complex three-dimensional shapes. It's long enough to have catalytic activity, the ability to speed up chemical reactions, including potentially its own replication. Some of the RNA molecules they created could actually catalyze the formation of more RNA, a critical step towards self-replication. And this chemistry doesn't work without wet-dry cycling. If you keep the nucleotides in constant solution, they don't polymerize efficiently. The equilibrium favors small molecules, not polymers. But wet-dry cycling drives the reaction forward. Each dry phase pushes the chemistry toward polymer formation. Each wet phase allows the polymers to interact, to fold, potentially to function. It's a ratchet mechanism. Each cycle moves the chemistry forward, and it doesn't slip backward. But the University of Washington experiment was just one of many pieces of evidence. Let's look at the broader picture of how tidal pools could create the chemistry of life, step by step, molecule by molecule. First, you need the raw materials, simple organic molecules. Where did they come from on early Earth? Multiple sources. Asteroids and comets delivered organics. We've found amino acids in meteorites. Lightning in Earth's early atmosphere could synthesize organics from simple gases like methane, ammonia, and water vapor. The famous Miller-Urey experiment from 1953 demonstrated this. Hydrothermal vents on the ocean floor create organics through reactions between water and hot rock. So early Earth had a dilute organic soup, not enough to spontaneously generate life, but enough to provide raw materials. These simple organics, amino acids, small nucleotides, fatty acids, simple sugars, get swept into tidal zones. They accumulate in pools. Concentration increases during dry phases. Now they need to react to form more complex molecules, proteins from amino acids, RNA from nucleotides, lipid membranes from fatty acids. This is where the details matter. Consider nucleotide polymerization, the formation of RNA. This requires energy and specific chemical conditions. In pure water, it's thermodynamically unfavorable. But add montmorillonite clay and the nucleotides adsorb to the surface. The clay provides a scaffold that holds nucleotides in the right orientation. It stabilizes reactive intermediates. During dry phases, the loss of water shifts the equilibrium dramatically. Nucleotides begin to link through phosphodiester bonds, the same bonds that hold RNA together in living cells. Magnesium ions, common in seawater and tidal pools, catalyze the reaction. The chemistry proceeds. RNA chains grow. Jack Szostak at Harvard has been studying this for decades. His research shows that once you have short RNA molecules, they can encapsulate inside lipid vesicles, primitive cell membranes. Fatty acids, another simple organic compound delivered by meteorites or synthesized in hydrothermal systems, spontaneously form spherical vesicles in water. These vesicles can trap RNA inside. Now you have something resembling a primitive cell, genetic material inside a membrane boundary. Szostak's lab demonstrated that these protocells can grow. If you add more fatty acids from outside, the membrane expands. If the vesicle gets large enough, physical agitation, like the churning of waves in a tidal pool, can cause it to divide into two smaller vesicles, each containing some of the original RNA. This is protocell division. It's not true biological reproduction yet, but it's a step in that direction. Matthew Powner at University College London has shown that the building blocks of RNA, ribonucleotides, can be synthesized from even simpler precursors in conditions plausibly present in tidal pools. Starting from just hydrogen cyanide, formaldehyde, and phosphate, all of which would have been available on early Earth, his team synthesized citidine ribonucleotides through a series of reactions driven by UV light and wet-dry cycling. This is powerful evidence that the chemistry of life doesn't require impossibly lucky accidents. It requires the right conditions, conditions that tidal zones provided. David Deamer at UC Santa Cruz has focused on lipid membranes. His experiments show that fatty acid vesicles can form spontaneously in tidal pool conditions and that they're stable through multiple wet-dry cycles. In fact, the cycling helps. During dry phases, lipids concentrate and form multi-layered structures. During wet phases, these structures expand into vesicles. The process naturally produces membrane-bound compartments, primitive cells, without any biological machinery. Just chemistry and physics responding to the tidal rhythm. John Sutherland at the MRC Laboratory of Molecular Biology in Cambridge has perhaps gone the furthest in demonstrating prebiotically plausible chemistry. His team has shown that you can synthesize not just nucleotides, but also amino acids and lipid precursors in the same set of reactions, starting from simple molecules like hydrogen cyanide and hydrogen sulfide in the presence of UV light and metal catalysts, like copper and iron, both common in early Earth rocks. These reactions work best under wet-dry cycling conditions. The chemistry is complex, but it's driven by physical processes, not biology. What emerges from all this research is a picture of tidal pools as natural chemical reactors. They concentrate reactants. They provide catalytic surfaces in the form of clay minerals. They cycle between conditions that favor different types of reactions: synthesis during dry phases, interaction and selection during wet phases. They create compartments through lipid vesicle formation. They provide energy input through UV radiation, thermal cycling, and chemical gradients. And they do all of this automatically, repeatedly, reliably, for millions of years. Somewhere, in one of billions of tidal pools scattered across early Earth's coastlines, chemistry crossed the threshold into biology. A particular combination of RNA molecules emerged that could catalyze their own replication. Perhaps it happened in a shallow pool, rich in montmorillonite clay, where nucleotide concentrations reached extreme levels. Perhaps it happened in an estuary, where fresh water brought specific metal ions that acted as cofactors. Perhaps it happened near a hydrothermal vent, where additional energy and chemical reducing power were available. We don't know the exact location or the exact chemistry, but we know it happened, and we know tides made it possible. Because here's the key insight: this chemistry requires cycling. Static conditions don't work. A permanently wet ocean doesn't concentrate molecules enough. A permanently dry desert doesn't allow chemical interactions. But wet-dry cycling provides both. It concentrates during dry phases, enabling reactions that form polymers. It rehydrates during wet phases, enabling those polymers to function, to fold, to interact, to potentially catalyze further reactions. It's a ratchet mechanism that drives chemical evolution forward. And only tides provide this cycling naturally, predictably, everywhere along coastlines for geological timescales. No other planetary process matches it. Not volcanic activity, not impact events, not atmospheric cycling, only tides. Which means only planets with large, close moons can create the conditions necessary for this chemistry. Earth had such a moon. Mars didn't. Its moons are tiny. Venus has no moon. The gas giants have no solid surfaces. Earth was unique in our solar system. A rocky planet with liquid water, with a massive nearby moon, creating extreme tidal cycling in the era when life emerged. We are, quite literally, children of the tide. Every molecule in your body traces its lineage back to chemistry that happened in a tidal pool 4 billion years ago. The rhythm of the tides is written into the deepest levels of biochemistry, and that rhythm was provided by the moon. But life didn't stop in tidal pools. Once it began, once self-replicating molecules emerged and primitive cells formed, evolution took over. And the moon continued to shape that evolution for the next 4 billion years, leaving evidence we can read today in rocks, in fossils, in the very structure of ancient organisms. The oldest potential evidence of life on Earth comes from rocks in Isua, Greenland, dated to 3.7 billion years ago. These rocks contain carbon with isotopic ratios that some scientists interpret as biological, carbon that was processed by living organisms. The evidence is contested because it's so ancient and the rocks have been heavily altered. But if correct, it means life existed just 800 million years after Earth formed. That's remarkably fast. It suggests that given the right conditions, which tides provided, abiogenesis happens relatively quickly in cosmic terms. By 3.5 billion years ago, the evidence becomes unambiguous. In the Pilbara region of Western Australia, there are rock formations called stromatolites. These are layered structures built by microbial mats, communities of bacteria that trap sediment and precipitate minerals as they grow. Modern stromatolites still form today in places like Shark Bay, Australia, and the Bahamas, so we can observe the process directly and compare it to ancient specimens. What makes stromatolites so important for our story is that they record tidal cycles. Each layer in a stromatolite represents a period of growth. The thickness of layers varies in regular patterns because microbial growth rates varied with environmental conditions. During high tide, when the microbial mat was submerged, growth was fast. During low tide, when it was exposed, growth slowed or stopped. This creates daily layering. But there's also monthly layering corresponding to spring and neap tides, the stronger and weaker tides that occur when the moon is new or full versus when it's at quarter phase. And there's annual layering corresponding to seasonal changes. Scientists have counted these layers in Pilbara stromatolites. The daily layers are clearly visible under microscopy. When you count them between monthly patterns, you find that 3.5 billion years ago, there were more days per month than today. Earth was rotating faster. Days were perhaps 18 hours long. The moon was closer, perhaps 250,000 kilometers away, instead of 384,000. Tidal ranges were 30 to 40% larger than today. These numbers match predictions from tidal evolution models perfectly. The stromatolites are fossilized tidal rhythms. They're proof that tides shaped early life. But stromatolites tell us something else even more important. They show that life flourished in tidal zones. These weren't organisms hiding in the deep ocean or buried in sediments. They were surface dwellers, exposed to tidal cycling, thriving in exactly the environments where tides were strongest. The rhythm of the tides structured their entire existence. They grew during submersion. They went dormant during exposure. Their metabolism, their biochemistry, their very cellular processes evolved in sync with tidal cycling. This pattern persisted for billions of years. As Earth's day lengthened and the moon receded, life tracked these changes. Organisms adapted to whatever tidal regime existed in their era. The moon didn't just create life, it paced evolutionary history. By 2.4 billion years ago, something revolutionary happened, the Great Oxidation Event. Cyanobacteria, photosynthetic bacteria that split water molecules to harvest energy, releasing oxygen as waste, had evolved perhaps 100 million years earlier. But for a long time, the oxygen they produced was immediately consumed by reactions, with iron dissolved in the oceans and volcanic gases in the atmosphere. Earth was a reducing environment. Free oxygen couldn't accumulate. Then, around 2.4 billion years ago, the balance tipped. Cyanobacteria had produced so much oxygen for so long that the chemical sinks became saturated. Iron in the oceans rusted out, forming massive deposits called banded iron formations, layers of iron oxide alternating with silica that you can see in places like Lake Superior in North America and the Karijini Ranges in Western Australia. Once the ocean iron was used up, oxygen began accumulating in the atmosphere. Within perhaps 50 million years, atmospheric oxygen levels rose from essentially zero to perhaps 1% of current levels. This was catastrophic for anaerobic life, organisms that couldn't tolerate oxygen. Most died out. But for aerobic organisms that could use oxygen for metabolism, it was an explosion of available energy. Oxygen respiration produces far more energy than anaerobic processes. Complex life became possible, and tides helped make this happen. Here's how. Oxygen-producing cyanobacteria lived in shallow waters where sunlight could reach, including tidal zones. The oxygen they produced would dissolve in surrounding water, but oxygen is toxic to many microbes, so it needed to be dispersed. Tidal currents were one of the main mechanisms for mixing oxygenated water with the broader ocean. Strong tides, remember the moon was still closer than today, creating tides perhaps 20% stronger than now, would flush oxygenated water from coastal zones into deeper waters. This prevented local oxygen concentrations from becoming so high they'd poison even the cyanobacteria themselves, and it distributed oxygen throughout the ocean, allowing aerobic organisms to spread. The banded iron formations themselves showed tidal signatures. The alternating layers of iron oxide and silica have rhythmic patterns suggesting they formed in response to tidal cycling, bringing iron-rich deep water up into oxygenated shallow zones, where it would rust and precipitate. The bands record millions of years of tides mixing the ocean, gradually oxidizing all the dissolved iron, setting the stage for an oxygenated atmosphere. Fast forward to 717 million years ago. Earth enters a period called Snowball Earth. Geological evidence suggests the entire planet froze. Glaciers reached the equator. Ice covered the oceans from pole to pole. This should have been a mass extinction event. How did life survive under global ice cover for tens of millions of years? Tides might have been part of the answer. Even under kilometers of ice, Earth's oceans would continue experiencing tides. The ice would flex and crack. Tidal stresses would create fractures and pressure ridges. At the boundaries between ice sheets and continents, tidal forces would generate massive stresses, possibly keeping some areas of open water. Hydrothermal vents on the seafloor would continue operating, providing heat and chemicals. Tidal mixing would distribute nutrients from these vents throughout the under-ice ocean. Microbial life could persist in this environment, clustering around vents and in zones where tidal cracking allowed some exchange with any thin atmosphere remaining above the ice. When Snowball Earth finally ended, around 635 million years ago, probably due to volcanic carbon dioxide accumulating in the atmosphere until the greenhouse effect became strong enough to melt the ice. Life rebounded quickly. Within 40 million years, we see the first evidence of complex multicellular organisms, the Ediacaran fauna. These are strange creatures, unlike anything alive today. Many had fractal, leaf-like body plans. They lived on the seafloor, possibly absorbing nutrients directly through their skins since they had no clear mouths or digestive systems. And many Ediacaran fossils are found in what were clearly tidal or shallow marine environments. Sites like Mistaken Point in Newfoundland preserve entire Ediacaran communities buried by volcanic ash 575 million years ago. The sediments show features indicating tidal influence: ripple marks, mud cracks, layered deposits consistent with tidal deposition. The Ediacaran organisms lived in tidal zones. They experienced the rhythm of tides, just like the stromatolites billions of years earlier. This makes sense if you think about it. Tidal zones are among the most productive environments on the planet. They receive constant nutrient input from both land runoff and ocean currents. They have access to sunlight. They're dynamic, preventing stagnation. For organisms just figuring out how to be multicellular, tidal zones would be ideal nurseries. Then, 540 million years ago, came the Cambrian explosion. Over a span of perhaps 25 million years, an eye blink in geological terms, most of the major animal body plans we see today appeared in the fossil record. Arthropods, mollusks, echinoderms, chordates, everything. It's called an explosion because the fossil record goes from mostly simple forms to suddenly complex forms with hard shells, segmented bodies, eyes, predatory appendages, defensive armor. Something triggered a rapid burst of evolutionary innovation. Many factors contributed. Oxygen levels had risen high enough to support active, mobile organisms with high metabolic demands. The evolution of predation created an evolutionary arms race: develop armor or get eaten. The evolution of hard parts meant organisms could leave clear fossils, so the apparent explosion might partly reflect better preservation. But there's another factor. Tidal environments provided diverse ecological niches that rewarded specialization. During the Cambrian, Earth's day was about 22 hours long. The Moon was at roughly 90% of its current distance. Tidal ranges were about 25% larger than today. That might not sound dramatic, but it meant larger intertidal zones, more area exposed during low tide, submerged during high tide. This created a huge range of microenvironments. Some areas were exposed only during spring tides. Others were submerged only during spring tides. Some areas experienced daily exposure. Others were always submerged, but experienced strong tidal currents twice daily. Each of these microenvironments selected for different traits. Organisms in high intertidal zones needed to resist desiccation. They evolved tough outer coverings. Organisms in strong current zones needed to hold on. They evolved attachment structures or burrowing behaviors. Organisms in tidal pools needed to handle varying salinity, temperature, and oxygen levels. They evolved sophisticated regulatory systems. The diversity of tidal environments drove diversification of body plans and behaviors. Many of the iconic Cambrian fossils come from the Burgess Shale in Canada, deposited 508 million years ago. These fossils show exquisite preservation of soft tissues, allowing us to see internal anatomy. Many Burgess Shale organisms show adaptations consistent with tidal or shallow marine environments. Organisms with gripping appendages for holding onto rocks in currents. Organisms with sensory structures for navigating changing conditions. Organisms with armor for protection in crowded intertidal zones where encounters with predators were frequent. The Cambrian explosion happened everywhere in the oceans, but the epicenter was coastal and tidal environments. The Moon's tides created the ecological complexity that evolution filled with morphological complexity. Jump forward to 300 million years ago, the Carboniferous period. This was the age of giant insects and vast swamp forests that would eventually become coal deposits. Dragonflies with wingspans of 70 centimeters, millipedes 2 meters long. Why so large? Oxygen. Atmospheric oxygen levels reached 35% during the Carboniferous, compared to 21% today. Insects don't have lungs. They breathe through tubes called tracheae that deliver oxygen directly to tissues by diffusion. Diffusion is inefficient, which normally limits insect size. But at 35% oxygen, diffusion works well enough to supply much larger bodies. Why was oxygen so high? Multiple factors, but ocean circulation and tidal mixing played a role. The Carboniferous had extensive shallow seas covering continental interiors. These seas were strongly affected by tides. During this era, Earth's day was about 23 hours, and the Moon was at roughly 85% of its current distance, creating tides about 15% stronger than today. These tides constantly mixed the shallow seas, preventing stratification and keeping dissolved oxygen levels high throughout the water column. This supported enormous marine productivity, huge populations of phytoplankton and marine plants producing oxygen. Meanwhile, on land, the evolution of trees led to vast forests, especially in swampy coastal areas influenced by tides. Trees produced oxygen and sequestered carbon in their wood. When these trees died and fell into swamps, the waterlogged anaerobic conditions prevented decay, and the carbon stayed buried. Over millions of years, this removed carbon dioxide from the atmosphere and added oxygen. Tidal swamps were carbon burial machines, driving oxygen levels higher and higher. Life flourished in this high oxygen world, but the system was unstable. Eventually, fungi and bacteria evolved the ability to decompose wood efficiently. Carbon burial slowed, oxygen levels dropped, the giant insects disappeared. But while it lasted, the Carboniferous was Earth's most productive period, and tidal mixing was part of the engine driving that productivity. Move forward again to 65 million years ago. An asteroid 10 kilometers across impacts the Yucatan Peninsula. The energy release is comparable to 10 billion Hiroshima bombs. Tsunamis hundreds of meters high scour coastlines. Dust and soot block the sun for months. Temperatures plummet. Photosynthesis shuts down. The food chain collapses. 75% of species go extinct, including all non-avian dinosaurs. But life rebounds. Within 10 million years, biodiversity is back to pre-impact levels, and mammals begin their rise to dominance. Where did the survivors hide during the impact winter? How did ecosystems reboot? Tidal zones were refuges. Here's why. Tidal ecosystems are resilient to disturbance because they're naturally dynamic. Organisms living in intertidal zones already cope with extreme environmental variability. Temperature swings, salinity changes, periods of exposure and submersion. They're generalists, tolerant of stress. When global conditions went haywire after the impact, these organisms could handle it better than specialists from stable environments. Tidal zones also maintained some productivity during the impact winter. Even with sunlight blocked, tides continued bringing nutrients from the ocean. Detritus, dead organic matter, accumulated from the die-off and got swept into tidal zones. Decomposers and filter feeders could survive on this even without photosynthesis. Estuaries and salt marshes became reservoirs of surviving biodiversity. When sunlight returned and photosynthesis restarted, these coastal populations could spread back out, recolonizing devastated terrestrial and open ocean environments. Fossil sites from the Paleocene, the epoch immediately after the extinction, show that many early mammal species had close associations with coastal and riparian environments. The ancestors of whales evolved from land mammals living in tidal estuaries, gradually adapting to more aquatic lifestyles. Primates evolved in forests, but those forests likely expanded from coastal refuges where diversity survived the impact. The Moon's tides provided the resilient environments that allowed life to survive Earth's worst extinction event and reboot mammalian evolution. Throughout all of this history, from stromatolites 3.5 billion years ago to the recovery from the asteroid impact 65 million years ago, the moon has been slowly receding. Days have been lengthening, tides have been weakening, and life has tracked every change, adapting to each new regime. The fossil record preserves this. Tidal rhythmites from different geological eras show different day lengths, confirming the moon's recession. Growth bands in fossil corals from the Devonian period, 400 million years ago, show about 400 days per year, meaning 22-hour days. Cretaceous corals show 372 days per year, meaning 23.5-hour days. Modern corals show 365 days. The progression is clear, continuous, and exactly matches predictions from physics. The moon didn't just create the chemistry of life 4 billion years ago. It shaped the evolution of life at every stage. It provided diverse tidal environments that drove the Cambrian explosion. It powered ocean mixing that enabled the Great Oxidation Event and the high oxygen world of the Carboniferous. It created resilient coastal ecosystems that served as refuges during mass extinctions. Every major chapter of life's history has been influenced by tides, by the moon. And today, we can see this influence in living ecosystems. Let me take you to the coast. Stand on the Olympic Peninsula in Washington State at low tide. The rocky intertidal zone stretches hundreds of meters from the high tide line to the water's edge. Everywhere you look, there's life. Tide pools dot the landscape, each one a miniature aquarium. In one pool, a sea star, a starfish, clings to rock, its tube feet creating suction against the surge when the tide returns. In another pool, sea anemones cluster, their tentacles waving in the residual water, waiting to sting any small fish or shrimp that ventures too close. Barnacles coat the rocks in white patches. These creatures are arthropods, related to crabs, but they've evolved to cement their heads to rock and filter feed with their legs. Mussels cluster in dense beds, each one filtering liters of water per day, extracting phytoplankton. Kelp, massive brown algae, anchors to rocks with holdfasts and stretches upward, fronds swaying in the current when the tide is in. Every one of these organisms is exquisitely adapted to tidal rhythms. The sea stars time their feeding to tidal cycles. When the tide is in, they hunt for mussels and clams. When the tide goes out, they retreat to deeper crevices to avoid desiccation. The anemones retract their tentacles during low tide, forming blob-like shapes that retain moisture. When the tide returns, they bloom open again. The barnacles close their shells during exposure, trapping water inside, a personal ocean they carry through the dry period. When submerged, the shells open and the legs emerge to feed. These rhythms are so deeply ingrained that many intertidal organisms have molecular clocks synchronized to tidal cycles. Remove them to a lab with no tidal cues, and they continue to follow tidal rhythms for days or weeks, opening and closing, becoming active and dormant according to the schedule of a tide that isn't there. The rhythm of the moon is written into their genes, into their biochemistry, just as it was 4 billion years ago when life began in pools like these. Travel to Cornwall in southwest England. The tidal range here can exceed 10 meters during spring tides. At low tide, vast expanses of rock and sand are exposed. This is called the intertidal zone, and it's one of the most biologically productive habitats on Earth. The productivity rivals or exceeds that of rainforests in terms of biomass generated per square meter per year. Why? Because of nutrient input. Twice a day, the tide brings nutrients from the open ocean. Twice a day, runoff from land brings nutrients from terrestrial sources. Organisms in the intertidal zone get the best of both worlds. Algae coat the rocks in layers. Green algae high up where they're exposed to air most of the time. Brown algae lower down where they're submerged more often. Red algae in the deep pools where they're rarely exposed. Each species is specialized for a particular tidal height. This creates zonation, distinct bands of different species running parallel to the waterline. Walk from high tide to low tide, and you walk through a gradient of ecological niches, each shaped by how much exposure and submersion that zone experiences. Crabs scuttle through the zone, opportunistic predators and scavengers. Shorebirds, sandpipers, plovers, gulls time their feeding to low tide when invertebrates are exposed and vulnerable. Fish enter tidal pools during high tide to feed, then retreat to deeper water as the tide goes out. The entire ecosystem pulses with the rhythm of the tides. Twice a day, energy and nutrients flood in. Twice a day, organisms must cope with changing conditions. It's a dynamic equilibrium maintained by the moon's gravity. Now travel to the Chesapeake Bay on the eastern coast of the United States. This is an estuary, a place where a river meets the ocean. Fresh water from rivers flowing off the Appalachian Mountains mixes with salt water from the Atlantic. The salinity gradient creates unique chemistry. And the tides, though reduced compared to open coast because the bay is partially enclosed, still rise and fall about a meter twice daily. Estuaries are among the most productive ecosystems on the planet. The Chesapeake produces enormous quantities of biomass. Blue crabs, oysters, striped bass, countless species of fish and invertebrates. Why so productive? Nutrient input from both land and sea. Rivers bring nutrients from decomposition in the forests and fields. Tides bring nutrients from ocean upwelling and biological activity. The estuary traps and concentrates these nutrients. And the salinity gradient creates diverse microhabitats, each supporting specialized organisms. Juvenile fish use estuaries as nurseries. They're born in the open ocean, but they migrate to estuaries where food is abundant and predators are fewer. They spend their early lives in tidal creeks and marsh grasses, feeding and growing. When they mature, they return to the ocean. More than 70% of commercially important fish species on the US East Coast depend on estuaries at some point in their life cycle. Destroy the estuaries and you collapse fisheries hundreds of kilometers away. And estuaries exist because of tides. Without tidal mixing, estuaries would stratify. Fresh water would float on top of salt water, oxygen would deplete at depth, and productivity would crash. Tides prevent this. Tidal currents mix the water column, distributing oxygen, preventing dead zones. The same process that oxygenated Earth's oceans 2.4 billion years ago continues today in every estuary. Visit the Amazon River estuary, where the world's largest river meets the Atlantic Ocean. The tidal bore, a wave created by the tide pushing up the river against the current, can travel hundreds of kilometers inland. The fresh water from the Amazon carries enormous nutrient loads from the rainforest. The tide pushes ocean water inland, mixing salt and fresh. The result is a biological explosion. The Amazon estuary supports fisheries that feed millions of people. It's a breeding ground for countless marine species. And it exists because the moon creates tides powerful enough to push ocean water up a river, flowing at 200,000 cubic meters per second. These modern tidal ecosystems, Olympic Peninsula tide pools, Cornish intertidal zones, Chesapeake estuaries, the Amazon bore, are direct descendants of the environments where life began. The chemistry is more complex now. The organisms are more sophisticated, but the fundamental dynamics are the same. Tides bring nutrients. Tides create cycling between exposure and submersion. Tides maintain productivity. The moon continues to shape life on Earth, just as it has for 4.5 billion years. But there's a poignancy to this story, because the moon is leaving. 3.8 centimeters per year. The tides are weakening. Not noticeably in a human lifetime, the change is too slow. But over millions and billions of years, it adds up. 1 billion years from now, if humans or their descendants are still around, the moon will be 38,000 kilometers farther away. Tidal ranges will be perhaps 10% weaker. The intertidal zones will shrink. Productivity might decline. The rhythms that have structured life for eons will continue to slow. And if you enjoyed learning about this, I'd be grateful if you'd consider subscribing. It truly helps us continue exploring these deep questions about our cosmic origins. We're living in a temporary moment. The moon is at a distance where tides are strong enough to maintain vibrant coastal ecosystems, but not so strong that they're destructive. 4 billion years ago, tides were catastrophic, but created the chemistry of life. 4 billion years from now, if Earth and the moon still exist, which is uncertain given the sun's evolution, tides will be feeble. We live in the Goldilocks era of tidal history, but humanity isn't content to just observe. We're going back to the moon, and this time we're bringing the tools to finally answer the deepest questions about where we came from. NASA's Artemis program is designed to establish a permanent human presence on the moon. Artemis 3, scheduled for 2025, will land astronauts at the lunar South Pole. This location was chosen carefully. The South Pole has regions in permanent shadow, craters that never see sunlight because the moon's axial tilt is so small. Temperatures in these permanently shadowed regions drop to about -250 degrees Celsius, among the coldest temperatures in the solar system. And these cold traps have accumulated water ice over billions of years. Where did the ice come from? Comets impacting the moon over geological time. Each comet carries water. Most of it vaporizes on impact and escapes to space because the moon has no atmosphere and low gravity. But a tiny fraction, molecules that happen to bounce into permanently shadowed craters, gets trapped. Over billions of years, this adds up to potentially millions of tons of ice in polar craters. NASA's Lunar Reconnaissance Orbiter has mapped the South Pole in detail. Radar and spectroscopic data confirm the presence of water ice mixed with lunar regolith. Artemis astronauts will drill cores, extract samples, and analyze them. But this isn't just scientific curiosity. Water is the most valuable resource in space. It's heavy. You don't want to launch it from Earth if you can avoid it. But if you can mine it on the moon, you have drinking water for astronauts. You have shielding against radiation. Water is effective at blocking high-energy particles. And most importantly, you can electrolyze water into hydrogen and oxygen. Liquid hydrogen and liquid oxygen are rocket fuel. The same fuel the space shuttle used. The same fuel the Artemis lunar lander uses. If you can produce fuel on the moon, you don't need to bring all your return fuel from Earth. You can launch from Earth with just enough fuel to reach the moon, refuel there, and then have full tanks for the return trip, or for going onward to Mars. The Moon becomes a refueling station. This is called in situ resource utilization, and it's essential for any sustainable space exploration architecture. Artemis Base Camp, the planned permanent lunar outpost, will test all of these technologies. Astronauts will mine ice. They'll operate electrolyzers producing fuel. They'll test closed-loop life support systems that recycle air and water with minimal loss. They'll grow food in lunar greenhouses using regolith as growing medium. They'll construct habitats using lunar materials. Robots will sinter regolith using solar concentrators, fusing it into solid blocks for construction. Every system that needs to work on Mars will be tested on the Moon first. The Moon is close. It's 3 days away. If something goes wrong, Earth can send help. If a system fails, you can evacuate. Contrast that with Mars. Mars is 6 months away. If something goes wrong, you're on your own. There's no quick return. You have to fix the problem with what you have. Testing systems on the Moon reduces the risk for Mars missions. It's the proving ground. China has parallel ambitions. Chang'e 6 landed on the Moon's far side in 2024 and successfully returned samples, the first time anyone has done this. The far side is scientifically fascinating because it's geologically distinct from the near side. The near side has large, dark maria, volcanic plains formed by ancient lava flows. The far side has very few maria. It's older, more heavily cratered, and its crust is thicker. Samples from the far side might contain rocks dating back closer to the Moon's formation, better preserved because they've been less affected by volcanism and impacts on the Earth-facing side. Chang'e 7, planned for 2026, will also target the South Pole. It will deploy a rover and a hopping probe that can jump between small craters using springs, searching for ice deposits. Chang'e 8, scheduled for 2028, will test technologies for building a research station. The long-term Chinese goal is the International Lunar Research Station, potentially built in collaboration with Russia and other partners, as an alternative to the US-led Artemis program. We're entering a new era of lunar exploration. Multiple nations, governmental and private entities, returning to the Moon, not just for flags and footprints, but to stay, to build, to use lunar resources, to prepare for deeper space. But there's another mission, not to the Moon, but to another world shaped by tides that might be even more profound. Europa Clipper launched in October 2024. It's on a trajectory to Jupiter, arriving in 2030. Europa is one of Jupiter's large moons, slightly smaller than Earth's moon. But beneath its icy surface lies a liquid water ocean, perhaps 100 kilometers deep. More water than all of Earth's oceans combined. How does this ocean stay liquid so far from the Sun? Tidal heating. Europa orbits Jupiter in an elliptical orbit. As it moves closer to and farther from Jupiter, the strength of Jupiter's gravitational pull varies. This flexes Europa's interior, generating friction, producing heat. The same mechanism that heated early Earth's oceans. The same mechanism that keeps volcanic moon Io active. Europa's ice shell flexes by tens of meters with each orbit. That flexing keeps the interior warm enough for liquid water. And where there's liquid water and energy, there might be life. Europa Clipper will measure the thickness of the ice shell using ice-penetrating radar. It will sample the composition of the surface, looking for organic molecules brought up from the ocean by geological activity. It will fly through plumes, geysers of water vapor that erupt from cracks in the ice, and analyze their chemistry directly. And it will measure the magnetic field to confirm the ocean's depth and salinity. If Europa Clipper finds evidence of organic chemistry, of energy sources like hydrogen gas that could power metabolism, if it finds anything suggesting biological activity, it will revolutionize our understanding of life in the universe. Because life on Europa would be tidal life. Life powered not by sunlight, but by tidal energy. Life that arose in conditions similar to early Earth. Liquid water, tidal heating, mineral-rich chemistry from rock-water interactions. If life began twice in our solar system, in two different oceans both shaped by tides, it would suggest that tidal worlds are prime targets for finding life everywhere. This brings us to the biggest question of all. Are we alone? And how does the Moon's history help us answer that? January 15th, 2027. Mark that date. Remember it. Because on that day, something extraordinary happens. The Lunar Geophysical Network goes online. Artemis astronauts will have deployed seismometers across the Moon's surface. Not just one or two, but a comprehensive network covering multiple sites. Near side, far side, poles, equator. These aren't simple instruments. They're extraordinarily sensitive accelerometers, capable of detecting ground motion measured in nanometers, less than the diameter of an atom. They'll record moonquakes. They'll measure how the Moon flexes under Earth's gravity as it orbits. They'll detect the faint rumble of meteorite impacts happening anywhere on the lunar surface. And from all of this data, from months and years of continuous recording, scientists will extract something we've been trying to determine for half a century: the Moon's exact age. Not an estimate with error bars of plus or minus 100 million years. The actual age constrained to within 10 million years. Perhaps better, perhaps to within 5 million years. Why does this matter so profoundly? Because 10 million years of uncertainty in the Moon's age translates to enormous uncertainty in Earth's early history. Right now, we know the Moon formed approximately 4.5 billion years ago, based on radiometric dating of lunar samples. But that 100 million year error bar encompasses critical events. Did the Moon form 4.55 billion years ago, meaning Earth's surface could have solidified and cooled relatively quickly? Or did it form 4.45 billion years ago, meaning the magma ocean phase lasted longer and stable oceans formed later? This isn't academic hair-splitting. This determines when life could have begun. We have chemical evidence, those zircon crystals from Western Australia, suggesting liquid water existed on Earth's surface by 4.4 billion years ago. We have isotopic evidence from rocks in Greenland, suggesting life existed by 3.8 billion years ago. If those dates are correct, life emerged within 600 million years of Earth becoming habitable. That's fast. Remarkably fast. It suggests that abiogenesis, the emergence of life from non-living chemistry, isn't some incredibly improbable fluke requiring billions of years of lucky accidents. It's something that happens relatively quickly when conditions are right. But if the Moon formed earlier than we think, if Earth cooled faster than we think, that 600 million year window shrinks. Maybe life emerged in 300 million years, maybe 200 million. The faster it happened, the more likely it is that life is common in the universe. Because if life can arise that quickly given the right conditions, then every planet with liquid water and a large moon creating tidal zones becomes a candidate for life. The galaxy might be full of life. Conversely, if the moon formed later than we think, if Earth took longer to cool, maybe life didn't emerge until 3.5 billion years ago. That's a billion-year gap from planetary formation to life. That suggests abiogenesis is difficult, requiring specific conditions maintained over enormous timescales. In that scenario, life might be rare. We might be one of the few places in the galaxy where chemistry got lucky. The Lunar Geophysical Network will resolve this. By measuring how seismic waves propagate through the moon's interior, scientists can determine the moon's internal structure with unprecedented precision. They'll map the size of the core. Is it liquid or solid? They'll measure temperature gradients. How much radiogenic heat is still being generated by decay of uranium, thorium, and potassium in the lunar interior? They'll determine how much tidal heating occurred in the past when the moon was closer to Earth. All of these measurements constrain thermal models, and thermal models tell you how quickly the moon cooled after formation, and cooling rate determines age. There's another source of data that will be even more direct. Artemis astronauts will drill into the lunar regolith, the layer of dust and broken rock covering the moon's surface, at sites that are ancient and have been undisturbed for billions of years. Deep in this regolith, protected from cosmic radiation and solar wind by meters of overlying material, there are preserved samples of something extraordinary: Earth's early atmosphere. Here's how they got there. 4 billion years ago, when tides were extreme and Earth's surface was being constantly flexed and fractured by the moon's gravity, volcanic activity was intense. But more than that, the tidal forces were so strong that they could literally eject material from Earth's surface into space. During the most violent tidal surges, when kilometer-high waves crashed across continents and tidal stresses fractured the crust, gases from Earth's atmosphere and even material from the ocean could be blasted into space. Some of that material, moving fast enough, would escape Earth's gravity entirely, and some of it, by chance, by the geometry of the Earth-Moon system, would impact the moon. The moon has no atmosphere, no weathering, no plate tectonics. Material that lands on the lunar surface just sits there, accumulating, getting buried slowly by meteorite impacts and the gradual mixing of regolith. Drilling into ancient regolith means accessing a time capsule. Scientists will find particles that originated on Earth 4 billion years ago. They'll analyze the chemical composition. They'll determine what gases were in Earth's atmosphere during the era when life emerged. Was it mostly carbon dioxide and nitrogen, as we assume? Were there other gases? Methane from volcanic activity, hydrogen from water vapor being split by UV radiation? Were there any organic compounds? This is direct sampling of early Earth's atmosphere preserved on the moon. It's not guesswork or inference from models. It's data, hard data. And it will tell us precisely what conditions existed when tides were creating the chemistry of life in coastal pools. Combine that atmospheric data with the moon's precise age from seismology, and you get a complete timeline. You know when the moon formed. You know when Earth's surface solidified. You know what the atmospheric chemistry was at each stage. You know when liquid water became stable. You know when organic chemistry could have started becoming biochemistry. You know when life emerged. And you know how long it took. This is the Rosetta Stone for understanding life's origin. Not on Earth alone, but anywhere. Because once you know how long abiogenesis takes under specific conditions, you can assess every other planetary system. You can look at exoplanets, planets orbiting other stars, and say, this one has liquid water. It's been stable for 1 billion years, but it has no large moon, so it has weak tides. Probability of life? Low. That one has liquid water and a large moon, and it's been stable for 500 million years. If life can emerge in 300 million years, this planet might have life. If it takes 1 billion years, it's too young. The detection of exomoons, moons orbiting exoplanets, is just beginning. The first tentative candidates were announced in the past few years. Kepler 1625b is a possible Neptune-sized moon orbiting a gas giant. Kepler 1708b is another candidate. The data is noisy and confirmation is difficult because moons are small and their gravitational effects subtle. But technology is improving. The James Webb Space Telescope and future missions like the proposed Large UV Optical Infrared Surveyor will be able to detect exomoons around many planets. When we have statistics, when we know what fraction of Earth-like planets in habitable zones have large moons, we'll know how common Earth-like tidal environments are in the galaxy. If large moons are common, then tidal worlds are common, and perhaps life is common. If large moons are rare, then systems like Earth-Moon are unusual, and we might be correspondingly rare. But it goes deeper. When we search for biosignatures, signs of life on exoplanets, we look for oxygen in atmospheres, methane in disequilibrium with carbon dioxide, phosphine, dimethyl sulfide. These are gases that biological processes produce, but that atmospheric chemistry would destroy quickly without continuous replenishment. If you detect them, it suggests biology. But you have to be careful, because there are non-biological sources too. Oxygen can be produced by water vapor photolysis if a planet loses hydrogen to space. Methane can come from volcanism. Now imagine refining the search. You're looking at an exoplanet. It has oxygen and methane in its atmosphere. It has liquid water, good candidate for life. But does it have a large moon? If yes, it has strong tides, which means productive coastal ecosystems, which means if life exists, it's probably abundant and diverse. Prioritize this planet for follow-up observation. If no moon, or only a small moon, tides are weak. Life might still exist, deep ocean vents, subsurface aquifers, but it's probably less abundant, less likely to produce detectable atmospheric biosignatures. Lower priority. Tidal dynamics become a criterion for assessing biosignature reliability. It's not just about finding water and oxygen. It's about finding the environmental dynamism that makes life productive and diverse. We're not looking for planets in isolation anymore. We're looking for planetary partnerships, systems where a planet and its moon have co-evolved to create habitable environments. Earth and Moon are the template. And 2027 is when we read that template with precision we've never had before. When we finally decode the timing of our own origins and use it to search for life elsewhere. But there's something more immediate, more tangible, something that brings this story from cosmic timescales back to human timescales. Because while we're learning about our past, we're also deciding our future. The moon is leaving. 3.8 centimeters per year, right now. Measurable, real, happening as you listen to this. By the time you finish this video, the moon will be a few nanometers farther away than when you started. By the time you go to sleep tonight, it'll be micrometers farther. By next year, another 3.8 centimeters. In your lifetime, if you live 80 years, the moon will recede by about 3 meters. Not enough to notice. The moon will look the same size. The tides will be the same height. But the process continues. In 1 million years, 38 kilometers farther. In 10 million years, 380 kilometers farther. 1/10 of 1% more distant, tides imperceptibly weaker. In 100 million years, 3,800 kilometers farther. 1% more distant, tides a few percent weaker. In 1 billion years, 38,000 kilometers farther. 10% more distant, tides noticeably weaker, intertidal zones smaller, coastal productivity declining. And in about 5 billion years, the process will stop. Not because the moon reaches some maximum distance, but because the sun will have evolved into a red giant, expanding to perhaps Earth's current orbital radius, possibly engulfing both Earth and Moon. Long before that, within 1 billion years, the sun's increasing luminosity will trigger a runaway greenhouse effect on Earth. The oceans will evaporate. The planet will become sterile. Any life that still exists by then will either have migrated elsewhere to other moons, other planets, other star systems, or will have gone extinct. But before that happens, there's another milestone. In about 2 billion years, Earth's rotation will have slowed to the point where one side always faces the moon, just as one side of the moon always faces Earth now. Earth will become tidally locked. At that point, the moon will stop receding because there will be no more tidal friction. The tidal bulge will be permanently aligned with the moon, rotating at the same rate. Days will be about 47 current hours long. From one hemisphere of Earth, the moon will hang motionless in the sky, never rising or setting. From the other hemisphere, the moon will never be visible at all, and tides will be far weaker because Earth's rotation will no longer be grinding against the tidal bulge. That's the end game. Tidal locking, the eventual cessation of the process that created us. The rhythm that has structured life for 4.5 billion years will fade to a whisper and finally stop. The partnership between Earth and Moon will end, not through separation. The moon will still be there, locked in mutual orbit, but through synchronization. No more dynamism, no more cycling, just stasis. We're living in the dynamic era, the era when tides are strong enough to matter, but not so strong they're destructive. The era when days are long enough for complex life, but short enough that we experience multiple cycles within a lifetime, within a year, within an evolutionary timescale. The Goldilocks era of Earth-Moon history. 4 billion years ago, you could have stood on a shoreline, if you could somehow survive the heat and the toxic atmosphere and the crushing tides, and watched the moon race across the sky, rising and setting 4 times a day, dragging kilometer-high waves behind it. The planet was a crucible. The conditions were extreme, but in that extremity, chemistry found a way to become life. Today, you can stand on any coastline and watch gentle tides rise and fall twice a day. The Bay of Fundy in Canada sees 16 meters. Most places see 1 to 3 meters. The moon hangs in the sky, placid, moving slowly, completing one orbit every 27 days. The conditions are calm, but that calmness is built on 4 billion years of tidal sculpting. The ecosystems we see today, tide pools, estuaries, intertidal zones, are the descendants of the environments where life began. The productivity, the biodiversity, the resilience of coastal systems all trace back to tidal processes initiated when the moon was young and close. 1 billion years from now, if any organism is present to observe, the tides will be feeble. The moon will be smaller in the sky. Days will be longer. The intertidal zones will be narrow strips, not the expansive productive regions they are today. Life will persist. Evolution is resourceful. But the tidal engine that drove so much of life's history will be winding down. We live in the middle, in the brief window when tides are neither too strong nor too weak, when the moon is neither too close nor too far, when the planet is habitable, not just in terms of temperature and atmosphere, but in terms of the dynamic processes that maintain habitability, the cycling, the mixing, the rhythm. You are here because of an improbable series of events. A Mars-sized planet had to form in the inner solar system at the right time. It had to collide with Earth at the right angle and speed, not head-on, which would have destroyed both planets, and not too oblique, which would have been a glancing blow without sufficient energy transfer. The debris had to coalesce at the right distance, close enough to create strong tides, but outside the Roche limit so the moon could form. Earth had to retain enough water after the impact to form oceans. The moon's recession had to be fast enough initially to move it away from the destructive extreme tide regime, but slow enough that tidal zones remained productive for billions of years. Change any one of these parameters, and the outcome is different. No moon, or a smaller moon, or a moon that formed farther away, and tides are weak. The chemistry of life doesn't concentrate in coastal pools. Abiogenesis doesn't happen, or happens much later, or happens differently. The evolutionary history diverges. The organisms that eventually evolve, if any do, are fundamentally different. You exist because a series of cosmic accidents happened to create a planetary system with the right properties. The moon shaped Earth. Earth shaped life. Life shaped evolution. Evolution shaped intelligence. Intelligence shaped consciousness. Consciousness shaped the ability to look back at this entire chain of causation and understand it. To recognize that we are the moon's children. That our existence is contingent on that ancient collision, that debris disk, that coalescing sphere of rock that has hung in our sky for 4.5 billion years, creating the tides that made us possible. The greatest gift the moon has given us isn't just life. It's not even the stable climate and the tidal ecosystems and the evolutionary pressures that led to complex organisms. The greatest gift is the knowledge that these things are temporary, that the forces which create habitability don't last forever, that companions, even companions as faithful as the moon has been, eventually depart, that everything ends. This is a hard truth, but it's also a liberating one. Because if we understand that habitability is temporary, we understand that life cannot remain on a single world indefinitely. The moon is teaching us, through its slow recession, through its measurable abandonment, that the future of life requires motion, migration, the willingness to leave home. Humanity is beginning to learn this lesson. We're going back to the moon, not just to visit, but to stay, to build habitats, to extract resources, to use the moon as a stepping stone to Mars, to the asteroid belt, to the outer solar system. We're developing technologies for closed-loop life support, for in-situ resource utilization, for surviving in environments that are fundamentally hostile. We're learning to be a spacefaring species. And when we go to Mars, we'll carry the lessons of the moon with us. Mars has no large moon. Phobos and Deimos are captured asteroids, tiny, with negligible tidal effects. Mars has no tides. Its climate is harsher, more variable, because it has no large moon to stabilize its axial tilt. Mars once had water, perhaps oceans, but it lost them because it's smaller and cooled faster and lost its magnetic field, allowing the solar wind to strip away its atmosphere. Mars is what Earth might have been without the moon. A dead world, or nearly dead, with perhaps microbial life clinging to subsurface aquifers, but no surface biosphere. We'll terraform Mars if we can. We'll give it an atmosphere, perhaps by releasing carbon dioxide from the polar ice caps, creating a greenhouse effect to warm the planet. We'll bring water from comets or from Jupiter's moons. We'll establish ecosystems. But Mars will never have strong tides. It will never have the dynamic coastal zones that made Earth so fertile. Mars will be habitable, but it will be a different kind of habitability, one we have to maintain actively, artificially, because the natural processes that sustain Earth don't exist there. And when we go to Europa, when we finally send a mission capable of penetrating the ice and exploring the subsurface ocean, a mission perhaps launching in the 2030s or 2040s, we'll be looking for tidal life. Life that evolved in darkness, powered not by sunlight, but by the heat generated by Jupiter's gravitational flexing. If we find life there, it will confirm what the moon has been teaching us. The tides are a universal driver of biology. That wherever you have liquid water and tidal energy, you have the potential for life. And when we look at distant star systems, at exoplanets orbiting other suns, we'll prioritize those with large moons. Because we'll know those are the systems most likely to have produced life. Systems where a collision, like the Theia impact, created a partnership, where a planet and its moon have danced together for billions of years, creating tides, creating rhythms, creating the conditions for chemistry to become biology. We are children of the tide. That's not a metaphor. That's biochemistry. The wet-dry cycling that concentrated the molecules that became life happened in tidal pools. The evolutionary pressures that shaped complex organisms happened in tidal zones. The ecosystems that sustain us today are powered by tidal mixing. The moon made us. And now the moon is teaching us how to leave. Because the lesson of the moon's recession isn't just that things end. It's that before they end, they can create something extraordinary. A collision created a partnership. The partnership created conditions. Those conditions created chemistry. Chemistry created biology. Biology created complexity. Complexity created consciousness. And consciousness created the understanding that this entire chain is temporary and precious, and must be preserved by spreading beyond its point of origin. The moon won't be close forever. Tides won't be strong forever. Earth won't be habitable forever. But life, if it survives, if it spreads, if it carries the lesson of the tides to other worlds, can continue. Not as earthly life, eventually. After enough time and enough evolutionary divergence on different worlds, the descendants of Earth life will be as different from us as we are from the bacteria in those first tidal pools. But the chain will be unbroken. The lineage will continue. And somewhere, on some distant world, organisms will experience tides, maybe from a large moon, maybe from a close binary star, maybe from some gravitational configuration we haven't imagined. And those tides will shape them just as Earth's tides shaped us. January 15th, 2027. The Lunar Geophysical Network goes online. Seismometers begin recording. Data flows back to Earth. Scientists begin the analysis that will tell us exactly when the moon formed, exactly when life could have begun, exactly how fast abiogenesis happens under tidal conditions. That data will guide the search for life elsewhere. It will tell us where to look, what to look for, how to interpret biosignatures. It will tell us whether we're alone or whether the galaxy is full of tidal worlds where chemistry has crossed the threshold into biology. The moon is waiting. It's been waiting for 4.5 billion years, carrying the evidence of our origins in its rocks, in its internal structure, in its recession rate. We're finally ready to read that evidence, to understand the full story of how a collision created a partnership, how a partnership created tides, how tides created life, how life created us. The answers are waiting, and we, after 4.5 billion years of evolution, after all the extinctions and radiations and adaptations, after climbing from tidal pools to savannas to cities to space, we're finally ready to ask the right questions. The moon made us. Now we honor that gift by becoming what the moon has always been, a companion, not to Earth alone, but to life itself, carrying it forward, spreading it outward, ensuring that the chemistry that began in tidal pools 4 billion years ago continues for 4 billion more, on worlds we haven't discovered yet, under skies we haven't seen. Thank you, Moon.